if you forget something, still, like it doesn't matter because it's in. So good. Now you're recording, we're all good. Yeah, that's your strong homotopy equivalence. A weak homotopy equivalence means nothing but X is weakly homotopy equivalent to Y if your all homotopy groups are equivalent. There is something called as Whitehead lemma that tells you that if two CW complexes are weakly equivalent, they are also actually homotopy equivalent, meaning that these homotopy groups and these weak equivalence notions capture more sensitive information than your homology.
I need to correct it
Yeah.
slightly. The weak homotopy equivalences, you have defined the homotopy groups is, well, depends on the base point. So it's actually, you have a map from X to Y, so that
Uh-huh.
for each point inside X, pi I of X with respect to that base point is the same as pi I of Y with respect to F little x. So it's more than what you said, basically. So you have to
Yes.
take in count in the base point inside.
Yes. 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 Yes.
Yeah, I mean, I think part of what he's saying is that it needs to come from a map, right? Like
Yeah,
it can't just
it
be
has to come from that.
right.
Yes, right.
Otherwise,
It is coming from induced map, yes, from X to Y, X dot to Y
No,
dot.
no, you have to. Well, yeah, but like we don't generally say this. It's still it's different. No, it's not point to point. It's different. It's not what you said. It's not. It's now. It's not what you write here. It's you have
Okay.
to like really literally write it every step. You have a map from X to Y. Let's say it's F. Yes, you have denoted.
Let's go. Let's go right here.
Yeah,
Yeah,
let's go
X to
write
Y.
it. So
Yeah, F.
it doesn't need to preserve the base point. So that's very important. Now,
Okay.
it doesn't need to preserve the base point. Now you have little star for
Uh-huh.
every pi I,
Uh-huh.
for every pi I of
Uh-huh.
x,
I
small x,
see.
yeah, small x, you need to know it. No, let's don't do dot. Let's don't do dot.
Okay.
Yeah, small x.
Mm-hmm.
And goes to pi I of y,
F of
f
X.
of x, yes, f of x for
Yeah.
each point x inside big X. Now, this is the weak homotopy equivalence.
Oh, so you need for every X, not only
Yes,
for one X.
no, it's not for one.
Yeah.
Because we can
Yeah.
think of,
Yeah. Yeah.
suppose we have X to be two disjoint circles,
Mm-hmm.
Y to be only one circle, then
Uh-huh.
it's certainly not homotopy equivalent. Because one has two disjoint
Right,
components, the
right,
other
right,
one.
right,
But
right,
if you
right, right.
don't
Mm-hmm.
consider all the points, then you say they are weak equivalent. No, that's not true.
Right, 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 right. Absolutely. Yes, makes sense. Yeah. Yeah, you have to be a little bit careful here and
Yeah,
define.
you have to be very careful here.
Yeah, yeah. So, yeah, if it is weakly equivalent, if it's coming from a map and it's inducing isomorphism on the homotopy group level for all the points. I'm going to highlight this for all the points. Okay, this is very important. Yeah, 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 yeah. Then it is then it is called weak homotopy equivalence. And yeah. Now something interesting. Let me show you something interesting. Oh, and by the way, I will leave this as another exercise here. Show that suspension X to loop Z, this guy is abelian. Hint is using Ekman Hilton. Because it shows up many times. I mean, I have encountered it many times, and I love this lemma. So I recommend it showing for those who haven't seen this. Prove that suspension X to loop. So suspension is X is something called as co-group. Loop space of Z has a group structure. Co-group to group, all the maps show that it makes a abelian group. Okay. Um, by using this, this gives you a one-line answer that pi n of X is abelian. Okay. Now, give me 1 second. I'm operating two things at the same time. So now let's talk about. So this is your this entire thing is essentially you're doing homotopy theory on topological spaces. I didn't give you long exact sequence. So if I have a homotopy fiber sequence, it induces a long exact sequence on homotopy groups. I'm not writing that down because for the purposes of this talk, I don't need that. But this is essentially some interesting fact about doing homotopy theory on topological spaces that one way or another, you my guys have encountered it, right? This is what we know by homotopy theory in general. I mean, in particular, like, but in 1950s, computing these homotopy groups are very hard. Computing this pi I of x, computation of this is hard. So for fibration sequences, it's a question of, for geometric topologies to give me a fibration, and then I find the long exact sequence from the fibration and compute it and compute some homotopy group, but that's a question of geometers. Now, in 1950s to 1960s, I would say 1950s, Kahn came up with a clever trick. What was the trick? Instead of doing geometry, he focused on doing combinatorics. And for that, he introduced something called as simplicial sets. I will define them, but for now, back of your mind, just think of them as a combinatorial gadget, a gadget that helps you compute homotopy groups. How? Let's see. So from topological spaces to simplicial set, we have a functor. That's your singular complex functor. So you guys have encountered this, like all of us, like even the first years, like given a topological space X, I can look at its singular singular set, right? Where singular X of n is defined to be the maps from your standard n simplex to X. This is how you define singular homology, right? By looking at free abelian group generated by at each level, and right. So you have so from here to here, from topological spaces to simplicial sets, you land by applying this functor, the singular sync functor. From simplicial sets, you can retrieve topological spaces by something called as geometric realization. Now, uh, I'm not defining this now. I will define this later after defining simplicial set. But back of your mind, just imagine that we have some simplices. We are we are gluing them accordingly to get a topological space out of it. And you always get a CW complex out of it. So it's a standard process. Okay. Now on topological spaces, as I just mentioned, you can do homotopy theory by looking at its homotopy groups and we have this notion of weak equivalence. You can invert all this weak equivalence, or another way of saying that you can take quotient by the weak equivalence relation, modulo, looking at two topological spaces, modulo weak equivalences. You land in a category called homotopy. Kahn came up with the idea of defining homotopy groups here. This is what Kahn's idea. And he proved that if you compute my way of homotopy group and then take its geometry realization of a topological space and compute the homotopy group in this topological space in the standard notion, those two coincide. And that means that I have a standard notion of homotopy groups here, and I can invert by modulo weak equivalences in some, analogous way, and we get homotopy category of simplicial sets. And we have our derived functors here. Just think of them when you were inverting the arrows, our functors will be restricted, right? In the restricted domain in a way. We're deriving the functors as well. Just think of that way. And denote them by R singular And I didn't say this, but this is that junction, and here this is your L. So left derived functor of the left adjunction, right derived from functor of the right functor, right adjunction, right side of that junction. These two will be adjunct, and more importantly, these two are isomorphic. Boom. So what does that tell you? That tells you any homotopical property you prove here, you're actually proving here in topological spaces. What does that mean? You can rewrite entire theory of topology, homotopy theory of topological spaces in terms of simplicial sets. And this is exactly what we're going to see. Analogous version of homotopy, notion of homotopy sets, homotopy theory in terms of simplicial sets. And that gives rise to your simplicial homotopy. This phenomena has a name. It's called Quillen adjunction. Quillen was Kant's postdoc student, and in 1967 he came up with clever, I would say clever, but a amazing way of like rewriting like homotopy theory. That is, instead of, you can do homotopy theory in arbitrary categories in terms, as long as we have three notions: fibration, cofibration, and weak equivalences, such that they satisfy some, some axioms. Not going to talk about that, but those axioms are very easy to see in topological spaces, and you can rewrite homotopy theory in arbitrary category. Nothing to do with simplicial sets in other categories as well. So, um,
Sorry,
so yeah,
but
let's talk. Yeah.
before you continue, in what sense is R singular and the other, geometric realization derived functor, like these are actually derived functors? I mean, usually when you
Yes.
say derived functor, you mean like, you have something that's maybe left exact and you take the right derived functor to compute its, higher cohomology, but like there's not really there's no linearity in this world. So what's meant?
I mean, the way I see that, the left-derived functors are your right Khan extension in the Khan extension setting. So this is a theorem. If it is a Quillen adjunct or something like that, then their left-derived and right-derived functors will induce isomorphism. And yeah, I can refer
Just
to that theorem,
like
but I can't.
what do you mean by derived though?
Right Khan extension, left-derived functors are right Khan extension here.
It's sort of something like this. So if you left or right, if you have a junction, left things do not always preserve the weak equivalences. Right
Uh,
do not always preserve right equivalences. So if we can find the closest functor, closest functor to the original functor, which preserve the weak equivalences, then it's called the left or right derived functor in the sense if it lives in the left or right. So Tor group is actually the left derived functor of tensor in this sense.
okay.
So it's a
Right.
generalization of Tor.
Gotcha.
There is no linear thing, but here it's literally a generalization.
Great. Thanks.
I just see them as right Khan extension and left Khan extension. You define them like Khan extension, right?
We are talking about the same thing. So left Kong extension is approaching to the original function from the left.
Yeah,
So it's the same thing. I just translated it in a non-mathematical language.
I see. Yeah, yeah. Yeah. But anyway, yeah. Um, so we can now start talking about this weak equivalences. I mean, sorry, we can start talking about this simplicial homotopy. That is the motivation for today's talk. That we can rewrite the homotopy theory of topological space in terms of simplicial sets. So let's start talking about simplicial sets. Before I go, any questions so far? Because we are entering the genre now. Okay, let's start. So, for defining simplicial set, we need a category of order sets is defined. This is the category of order sets denoted by this. I'm sure many of you have seen this already. 0, 1 to n without ordering on them. And maps between them, this is your objects, and morphisms are mapped between them, which are order preserving. Okay. Cool. Now out of all these maps, there are only two maps that those which are basically interesting. Let me write down those two maps. So this is your n. It will look like 0 less than 1 less than dot 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 I minus 1 less than I less than I plus 1 less than n. This is your n plus 1. So there are two ways of doing this. I mean, two way of okay, now let me write down the n plus 1 first. 1, 2, this 1 less than I less than n plus 1 n less than n plus 1, and this is your n minus 1. 0 less than 1 less than 2. Cool. Now, to map from here to here, you have to skip an element, right? If you want to, I mean, yeah, unless of course you are taking the identity map, just taking the direct inclusion. But if you are trying to take a non-trivial map, you have to skip an element here if you're trying to preserve the order. So 0 goes to 0, 1 goes to 1, 2 goes to 2 here, I minus 1 goes to I minus 1 here. Suppose you skip the ith element. This is denoted by your di. It's called cophase because we'll see why. And then similarly, you have to come from here to here n to n minus 1. Let me write down di here. You need to project two maps, two elements into the same place because you have less elements here. So let's say that the ith, this I element has been mapped twice and everything is working fine after that. This is denoted by Si. So either you can skip an element or you can project two elements into the same space, right? These are called elementary order preserving maps. These are the only two possible elementary or order preserving maps. Now, if I give you any map, f such that n to n, you can write that map in terms of these di and si's by skipping the elements or projecting the elements into the same spot. That's the only way you can preserve the order, right? So that means that any map phi can be written are generated by these di and these sj's. So if I study these di and sj's, that's good enough. That's all. And they follow through some kind of relation, some pattern. The pattern is I'm gonna copy them so that I don't have to write them. Where is it? Okay, yeah. This is what they will satisfy. These are the relations. Yeah, I think here it would be better if I show you by a picture that you drew last time. So think of this 0, and this is a motivation for geometry realization as well. yeah, think of this 0 as a point. This is your 0. Think of this 1 as 0 to 1. Now there are two ways of putting this 0 here. Either you go on this boundary or you go here. If you go here, this is your D1 and this is your D0. Cool. Same for 2. That's your 2 simplex. 0, 1, 2. There are three ways of putting this 0, 1 in the on the sides of this simplex. Over here, over here, over here. This will be your D2, this will be your D0, this will be your D1. Yeah, this 2 here. So whether you are thinking of them in terms of the maps here, D0, D1, D0, D1, D2, or thinking them of as an inclusion of this inclusion of geometry simplices, both are same. This is what I want you to realize. You think of them in a way, think of them in this geometric setting, but write them in this setting. That's all that's going on. And similarly for this S maps, the degeneracy maps or co-degeneracy maps, whatever. This 1, 0. This is your 2. There is only one way to get 0 out of it by squeezing this whole interval to 0. This is your S0. 1, 2. Now you have to either to get here, you have to either um yeah how do I say this? Yeah, you either have to, you know, what's the right word? Pinch this guy over here. No, slide, put this guy entire down. That will be your S1, and or pinch this side down. That is your S0. What is the right word here? Right English word? Squeeze it.
Contract? Is that what you're
Contract,
looking
yeah.
for?
Contract, yeah. Contract the 0 to side or 1 to side, then you land in 0, 1. Right? So there's are
Projection.
two options. Yeah. So again, think of them geometrically, but write them down in this setting. 1 to 0, 0, 0, so on. Cool. Now, with this setting, with these pictures in the mind, we are ready to define what a simplicial set is. It's a functor from opposite category of the order sets to sets, where n goes to your x of n denoted by this guy, xn, x sub n. Now what happens here, let's see in terms of these base maps. This is your di, you land in n plus 1. This is your si, you land in just call it sj, you land in n minus 1. Apply the functor x, xn plus 1, xn, xn minus 1. Now the arrows will be reversed. This will be your x dy, and this is your x sj. We denote this by d lower I, we denote this by s lower j. Now apply the x functor here, over here. Apply the x functor here on all of them. And look at this. They will give you relations. It's a contravariant functor, so we'll flip the direction of the composition. And again, I don't want to write that down. So there you go. I'm going to copy it. Just flip the direction down and you'll get these relations between them. Cool? So, given a functor, so simplicial set is a collection of sets such that they have these maps in between them such that they satisfy all these conditions. That's what your simplicial, let me zoom out. That's what your simplicial sets are. Now, whether you define them as a functor, now there is a two notions of two way of viewing simplicial set. One is the functor way, and another is this way, that is a collection of sets. Oops. Such that they have arrows in between. D0, this is your D1, and the opposite direction we have my is 0. D0, D1, D2, in the opposite direction we have S0, S1, so on and so forth, such that they satisfy these conditions. This is an equivalent way of seeing simplicial sets. Now time for some examples. The first example that should come to your mind is applying this functor. So we are looking at the contravariant functor from delta of two sets, right? Now look at this functor over here in the in this delta category itself, you know. The arrow, the dash is in the contravariant position, so it's a contravariant functor. It's a map between two finite sets, so it lands in sets. So it's a contravariant functor, right? It takes q to delta of q comma n, and this is denoted by delta n over here. This is your standard simplicial n simplex. Let's analyze them for a bit. No, add a few more pages. So your delta 0. We are looking at all the maps into 0. What's delta 0 comma? It's bleeding. Do you see this? It's bleeding on the iPad. How? No, it's good now. So 0 to 0, there is only one map, right? If you take delta 1 to 0, that's still one map. 2.0 and 1 goes to 0. There's just one map. Similarly, if you keep continuing the pattern, you will keep getting one map. So in some moral sense, it makes sense to call this delta 0 a point, right? Because it always gives you outputting a point. So let's call it a point. Are you following me or what? Like, so far? Good? Okay.
Yeah, so
Good.
far so.
Yeah. So, yeah. So, now let's look at delta 1. So delta 0 is a point. In back of your mind, it's in some moral sense. So back of your mind, you think of delta 0 as a point. Now let's look at delta 1. It's not that simple. I mean, if you keep inputting the points over here, let's do it. I did it. That delta 0 to 1. These are your two maps, right? So 0, and this is where you have 0 less than 1. You can either take 0 to 0 or 0 to 1. So these are your two maps. So on and so forth. If you do from 1 to 1, 0 to 0 1 to 0 1, or this is the only non-degenerate map, and other two maps are degenerate. Either have to take everything to 0 or take everything to 1. Three maps, but one honest map. Now, if you keep increasing them, you won't get any more non-degenerate maps, because you have to project more than I have more than the I have more elements in here, 0 1 to k, and I have less element here. I have to project more elements here, or over there. So you don't have any more non-degenerate maps, right? Now you can think this guy, this delta 0 1, these two maps, in terms of, so this is your two map. This is your 0 goes to 0, this is your 0 goes to 1. Think of them as 2 points. Call this 0, call this 1 if you have to. And look at what happens here. Let's take this entire thing out. If you apply, oh, okay. It also copied this guy. If you apply SG0 on the top row, apply S0 here, then you get, sorry, not S0, you apply D1. So basically you take 0 and 1 to the same point, 0. So you get 0 goes to 0 or 0 goes to 1. Here you have 0 goes to 0 only, and here you have 0 goes to 1 only. These are the only possible option here. So for this guy, 0 goes to 0 and 0 goes to 1. For this non-degenerate simplex, you can think of them as a morphism between this 0 goes to 0 to 0 goes to 1, this guy. And for that, you add a one-dimensional line here. I'm not making any sense here, right? So for these delta zeros, you add points. For this delta 1, you add interval. How do you add the interval? It is denoted by, it is determined by how you attach this, how do I say, how do you attach this, yeah, this non-degenerate simplex. That's all I have to say here. And so the point is, you, for each non-degenerate maps, so here this was your non-degenerate map, 0 goes to 0, 0 goes to 1. At the 0th level, those are your points. Here there is only one non-degenerate map, 0 goes to 0 and 1 goes to 1, and you attach them to 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 the vertices. And you can continue this process for delta 2. Now we have three non-degenerate maps at the 0th level, delta 0 to 2. I'm going to call them 0 1 2. Two maps coming from here, 0 1 0 1 2, like this, or no, actually three maps, 0 1 goes to 0, and then 1 goes to 2, or 0 goes to 1, 1 goes to 2, then 0. By the similar recipe that I explained very poorly, you attach this non-degenerate uh, one simplices here. And here you have just only one non-degenerate simplice, that is your identity. 2 goes to 2 identically. And for that you attach 1 2 simplex here. And for the higher one, again everything becomes degenerate. So you can't add anything more. I won't say can't, you don't add anything more. That's a better way to phrase it. So either you can think of them in terms of, so you can think this guy, this delta A, and this is the upshot of whatever I have discussed, as in terms of sets and the morphisms in between them, satisfying the conditions and all that, whatever. Or you can think of them as this geometric n simplex that you see in topology, like standard geometric n simplex. Both will convey the same thing. I think them in this way. This is the best way to say it. Think of them this, write them like this. This is your topology, and this is your simplicial sets.
So you like geometrical realization, right?
This is the geometric realization. This is the geometric realization of your standard like simplicial and sets. So this is, I'm giving you a like tour of geometric realization. That's all. This is what I'm trying to do. Are you guys happy with this so far? Like enjoying? Like anything? Any comments, questions? Let's take a break and have some questions.
So you mentioned in the quilling a junction, in the simplicial set, what are those weak equivalence morphisms? On the left side, I know it just induced the
Yeah, there are two ways of doing it. There is a dishonest way and there is honest way. Let me give you the dishonest way. The dishonest way is that you say two simplicial sets are weakly equivalent if you pass through their geometric realization and tell them they are weakly equivalent. There you go.
that's
That's the
that's
that's the cheap way of doing that. The honest way of doing that using Kant's infinite fiber. It's a, I don't know what it's called. There's a function. I didn't encounter that so far, but I will soon going to. So given this x dot, you can define this ex infinity functor. So it takes infinite subdivision of a simplicial set, if I read this correctly. And over here you can do something and compute its homology group in a way. It lands in ace abelian, if I'm not wrong, or if not, then you can make it land in ace abelian and compute the homology group somehow. And cool ensure that this can be bullshit. I don't know, so I don't want to make a promise on that. That this is same as your pi I of x. This is what cool ensure. That's why you can define it like that. But yeah, this is the honest way of doing it. But I have to check this out. Like this information, I have to check this out. I don't remember at the top of my head. Yeah, I don't want to erase it because yeah, it might be very, very wrong. Cool. Cool. Let's keep going. So we have defined our simplices in terms of simplicial sets, we are already getting there. So yeah, um, let's define now simplicial circle, because that's an important component of defining homotopy in topological spaces, right? So this is how you define simplicial circle. Or before that, you need to define what a boundary of a simplicial set is. Again, think of this in your back of your mind. It should be the actual boundary of a geometric simplex, that is your 0 and 1. What is this guy? This guy is your 0 and 1. The where I what do I mean by that is your two. Now what do I mean by that? Wait, let me see a good way to phrase it. Okay. Okay, let me motivate this in fact. Yeah. This thing is your 0 and 1, right? This is your standard one line, two endpoints of the line 0 and 1. Cool. You can think of this as a maps. I should not say equal. Think of them in terms of simplicial sets. That is a map from 0 to 0 and 0 to 1. You think of them way, and that is same as saying it is a map into 0 to 1 and 0 less than 1. That is same as saying it's a map from 0 to 1 and 0 to 1 by the which map? D0 map or D1 map? D1 map. And here, this is 0 to 1 by D0 map. Cool. Now, hey, you can, that is same as saying these are the maps from, this is a map, same as saying this is the map from delta of 0 to delta of 1. No, not this way. D0, D1, the induced map. So this 0 and this one in the covariant position. So their induced map will be in the same direction. Am I making sense, everyone? So let me write this down. So 0 to 1. Now delta of this guy, since this 0 is in the covariant position, will induce a natural map here in the covariant position. This is your D0. I'm not going to use a different notation because there are so many notations, so call this D0 itself. This is what I mean by here. Cool. That is same as saying this is your looking at image of D0 union image of D1. And this is how you define it. Are you convinced? Again, you're thinking them in terms of endpoints and you're writing them in terms of simplicial sets. Are you convinced or not?
Define the boundary. Okay.
This is your boundary of your standard simplicial set. Okay, one simplicial set. It is defined to be like this. Yeah, like this.
Oh, I see. I see. Yeah,
You
I
see the
got you.
motivation, right? So 0 and 1 can be think of as a maps between two simplices, standard simplicial sets. Now I'm writing. So let me give you another way. Standard motivation for this. So this is delta 1 is a simplicial set. I want to land this delta of D1 in a simplicial set. Now, how do I do that? You have to use the simplicial sets in the definition, right? This is how we're using them. Making sense now?
Yeah.
Cool. Thank you. And your circle S1 is delta 1 quotiented out by delta of day1. And guess what? This is your simplicial circle. And this is the geometry realization of the simplicial circle will be your actual circle in topology. So you got our second ingredient. We have we got our, actually no, not second ingredient. We have no second ingredient. So this is your intervals. We have translated our interval in terms of simplicial set. We have translated our circle in terms of simplicial sets. We can now, we are very in a good position to talk about homotopy. But before that, let's talk about, yeah, I do want to talk about homotopy right now, but before that, we should talk about some more examples.
I mean, so I mean, this is certainly a definition of the simplicial circle, but I mean, I feel like this is still more heavy-handed than it needs to be. Like you can certainly just write out the simplices like explicitly.
I like how.
I mean, it requires a little bit like a bit of a calculation or something, but um, like you know that it has like 1 0 simplex and
Yeah.
uh, a degenerate 1 simplex and a non-degenerate 1 simplex, and then everything 2 and higher are degenerate, and then you have to still write down what all the base and degeneracy maps are. But like
Right. Right. That's
this is doable, and I mean I think it's worthwhile to do too. Like if simplicial sets are something that's new to someone in the audience, then like I mean I'm not saying you have to do it right now, Crescendo. I'm just saying like this is a good
yeah,
exercise
yeah,
to.
yeah. This can be a good exercise.
I mean
Give
like
it a
I
simplicial. Yeah.
I think a lot of like the intuition you should have like in doing constructions and doing like working through this should come from topology. It should come from things like simplicial
Exactly.
complexes and whatnot. But in the end, like you end up having to do some computations, and I think doing those computations is where you really build your intuition for these things. So it's good to do.
Yeah. So what is the exercise? Give it a simplicial.
Like I mean, all
Uh,
you have to do to just actually write down the functor, right? Like actually write
yeah.
down what the simplices are, and like
Right.
as you said before, they're the morphisms in the simplex category are determined by just the base and or cobase and codegeneracy maps. So you just have to write down where they get sent, right?
But simplices. Yeah. Yeah. Simplices and DISIs.
Yeah.
Uh, nice. Yeah, it's a good exercise for that. Okay. Now let's define homotopy. We're in a good position to define homotopy, and I think we can end today by defining the homotopy. If I mean, I can go on, but let's see what the audience want. So, how do we define homotopy in normal topological spaces? We define like this, right? Now this is in your in top. We define like this: x cross y to y, two maps x to y, call them f0 and f1, are called homotopic if there exists a map from x cross I to y such that, let's write this down, x cross delta I to here, it's an inclusion. You either, I mean, standard inclusion, so 0 or 1, and such that this diagram commutes. Everybody agrees here?
Yeah.
That's your standard. Now here's the trick. We are translating this in terms of your simplicial sets. Let's do it. So think of this x now as geometry realization of some simplex. So let's write let's write that down. Think of this x as geometry realization of this simplicial set x dot. Interval is a geometry realization of one simplex, right? We just talked about it. These are your maps. These are inclusion. we just define your delta of D1. So it makes sense to talk about this guy. And yeah. Cool. Now, take this, take all this, bars out. So this is your simplicial set. Now, analogously giving a map from here to here, that's same as saying I have on the simplicial set level, I have these maps. And this guy now you can define. So this entire thing lies in simplicial set. So you can define morphism between two simplicial set that are homotopy equivalent. A homotopy between two morphism in simplicial set in this way. Are you guys happy? Are you ready to accept this as a definition?
Sorry, so a pedantic thing, but we actually have not defined what the product
Yeah,
of
the product is we defined it in the last class, so before the seminar. So yeah, I kind of like got zoned out. So yeah, we can define a product in a way here such that the product of this guy and geometry realization respect the products. So you will have this thingy. So this relation, so all of this will make sense, and you can define the homotopy of two simplicial sets in this way, and two simplicial set will define them as a homotopy equivalent if I have a map F and the other way map simplicial map G, such that their compositions in this notions of homotopy is equivalent to identities corresponding to identities, respective identities. I don't know which identity what, so then we call them the two spaces to be homotopy equivalent in simplicial sense. Cool.
Mhm.
Now let's talk about the constructions in simplicial, so this product and co-product stuff like that. The biggest benefit of using this simplicial set, you can define product and co-product very easily. Like they are very predictable. Those are just some product of the sets, product of the maps, product of, you know, they're predictable. That's all. So if your X and Y are two simplicial sets, I am trying to define the product here, the co-product here first. So what that should be, we have to give you the map at each level. That should be your the qth level of this simplex X and the yth level of simplex X and take their set co-product, right? And the maps in between them will be the maps in between the co-product with respect to the co-product. So nothing fancy. Similarly, you can define x cube cross y cube. Now, yeah, now we are trying to, rebuild our notions of homotopy theory in terms of simplicial set. And in homotopy setting, in topological spaces setting, we had something like this, right? We want to see something analogous here. Something analogous here. What do I mean by that? We want to see this guy. The simplicial set map. So X cross Y is a simplicial set. So map simplicial set maps, the maps in the simplicial category between X cross Y to Z should be same as, say, X cross. The internal Hom functor for now, let's denote it by map YZ. You want to see something like this, right? You need to define this guy so that you can write it like that. Some adjunction version here. So let's see how to define this guy now. How should we define this guy? For that, we use Unida. Choose Y to be X to be your standard simplicial Q set, standard Q simplex. Now replace the relation here, X cross Y cross delta Q, comma, Z. This is your simplicial set morphism. Yeah, delta Q. It's better to write it like this because I'm going to use Unida to here to map of Y comma Z. Remember, this is a simplicial set. That's a functor. This is also, I want this to be a simplicial set because that's how you get the morphism here. And a natural transformation between the simplicials, this guy, I mean, morphism in simplicial set is natural transformation between these two functors, right? That is one-to-one correspondence with the objects inside this guy. This is by Unida. Are you convinced here, or should I write down a little bit more simpler version?
Yeah, I'm okay.
Let me write down a little bit more simpler version, just for sake of bookkeeping. Simplicial set, this is your delta of Q. Take another simplicial set here. This is a functor, this is a functor. By Unida lemma, this is in the one-to-one correspondence with this xq, x of q, and that is your xq. Same thing we are doing over here. Okay. Now it makes sense to define this guy to be this guy. That's how you define it. There you go. That's your definition. In the notes, they are defining it out of the blue, but it's not out of the blue. It's very natural. Like if you just sit down and use the unit like once, this is your defined to be this, and that gives you your closed symmetric monoidal structure here. Where is it? Here. This will automatically make this guy closed symmetric monoidal. Note that we could not do something like this so easily in topological spaces because this is here we had Unida in our rescue. So that's a big feature of in terms of simplicial set. These features that makes it working with simplicial sets easy, that you can construct these limits, co-limits easily. I would say more predictably, naturally. Yeah. And for any closed monoidal category, again, this is another consequence of Unida. we have internal home, and we can coincide with the external home. So in particular for simplicial set, this will hold. This is another consequence of UNITA. For this is not really actually let's talk about it because you have done everything so rigorously. Let's talk about it. So what do you have to show here? So what does UNITA tell you? If you know everything about every morphism into an object or out of an object, you know the object. So let's talk about the every morphism into the object. Okay. If this holds, then we can conclude this holds, right? First, do you agree with this? That's really relevant. That's all. Now, apply A here and just let's see if it agrees or not. That's all. Plug in A here for all A. Let's go to the next page. Boom. Now you can use your adjunction here. So A2 map x cross y2 comma z is same as the maps from simplicial set maps from A cross x cross y to z. Right. Let me see the adjunction for a moment. Yeah. Simplicial set maps from here to here. Now, that is same as saying we have to do some permutation here. Wait, let me.
First move y to z, then move x, right? One by one, associative.
Yeah. What did you say? Yeah. First move
Just
y.
y to the right. Is I'm thinking
Yeah, yeah,
about
yeah. First move, yeah, yeah. First move y. Yeah.
I'm
First move
thinking
y here, then x there. Thank you, thank you. Yeah. Again by the adjunction, then you move that. There you go. Nothing special with this guy with simplicial sets. It's true in general. So there you go. True for all A, then you are done. Yeah. Then you are done. That's all. You have checked it. Yes, this holds. Erase the F. I have a quick question here, like for you guys, since you guys are expert. So what is the guarantee that this guy, you know, um, this guy will be a set itself? What is the guarantee here?
I mean, you're working in a small category, so its Hom spaces are sets, or morphism spaces are sets, right? Like definition of a category.
But that's your definition of I mean, for delta it is true, but for simplicial set, all the morphism between here to here, that may not be a set, right? I mean, it's not obvious.
Uh, I mean, it's a small category, so
What is a small? Like, which category are you calling small?
the category, or I guess, okay, so the category of simplicial sets need not be small.
Exactly.
Doesn't matter.
But
It's like the mapping space is so how do you say it? Mapping space you're thinking of as a monoidal category
Mm-hmm.
over simplicial set. So it's already contained the monoidal structure inside. But before the monoidal, you have to have the category before the monoidal structure. So that's why you have simplicial set. But this is a category, and a category Hom is only a set. It's not any other thing. It's only a set.
yeah, there like, you know, the class of objects could be large, but the
Hom is
actual it's still locally, like, yeah, I mean, yeah, it's still small, like the Hom spaces.
yeah, it's locally small.
Yeah.
How is it? Sorry, I didn't quite get it.
So in order to have a monoidal category, you must have a category before the monoidal structure. So you have to define the Hom set before the Hom complex.
Right, right.
So the first line is to be defined. It's saying the Hom complex is defined by some Hom set.
Okay. Okay, yes.
I mean, I think there's like a lot lower tech way of seeing this as well. Like just write down like all the possible data that a functor, like, you know, in the category of simplicial, like, or between simplicial sets could entail, and it's like inherently set theoretic. It just can't blow up, right? You say, oh well, it takes, you know, simplices to simplices. It takes, you know, one morphic, you know, the face and degeneracy maps to some combination of face and degeneracy map. Like everything is maps of sets, right? There's no way it blows up into something that's bigger.
Still trying to like be convinced with it, but
Right, like what is a functor? Or like, you know, what is a map between simplicial sets? Well, it has to do
yeah,
something
yeah.
to the like at the object level, and it has to do something at the morphism level. And at the object level, there's only, you know, it's some set, many maps.
Yeah.
And at the morphism level, again, it's just some set, many maps. So like the resulting thing is still, you know, a product of sets, which is still set. Or not product, but like some, you know.
Right. But the thing is that uh okay.
So actually, what I don't understand is your question. I answered your question in some aspect. I Colton answered it in another aspect. What was your question actually?
My question was that so you are want this guy map of X
You have a
Y
map.
to land in simplicial set, right?
Yes,
That
yes,
means
right.
that these levels they have to be landing in set. How do I know the maps in between these two simplicial sets are actually a set?
What do you mean? What do you mean? Is it the size issue or other things? Like Carlton was talking about the size issue, but I don't know if I should answer it in that way, or you just don't know why it's a set. Why it's a set, but not a simplicial set. So what was your question?
My question is like at the each level, this qth level, is it how is it a set?
Yes, yes, it has to be a set, right?
Right.
No, I still don't understand your question. Sorry about that.
Yeah, but how do we know this guy, all the
So
simplicial set maps between these two guys in a
are
set?
are you are you
Yeah.
comfortable with the notion that simplicial set is a category? Like there's like S set is a category.
Yeah.
Okay, so part of the definition is that the morphisms, sets are sets, right?
I
Like,
thought morphisms are defined this way, x0 to, x1, x2, this is a y0, y1. This is your f0, f1, so
Uh,
they commute with
no,
the.
no, no. A morphism is bunch of things. F consists of F0, F1,
Yeah,
F2,
yeah,
a lot of things.
yeah, yeah,
All
yeah.
these things all together is one thing instead of a bunch of things. Is only
Exactly.
one morphism.
That's one morphism, but how do we know the collection of all those morphism is a
It's not a space. It's not a space. The collection of all morphism between two simplicial sets is not a simplicial set.
yeah,
It's
that's fine.
never a simplicial set.
Mm-hmm. Mm-hmm. But is it a set? That's my
It's a
problem.
set. It's only a set. Like a bunch of things, it's a set. We don't like need to any structure on it.
It's a set. How do we know it's a set? That's the thing. Like
What do
that's
you
the
like,
mean? How do we know it's a
w-
set?
w-
Is it
w-
the size issue or
yeah, what's your concern for
yeah?
why
What's your
this could not
concern?
be a set? Where's your doubt?
how do you know? Like
A set is defined to be a collection of things, so it's a set.
I think this is a good exercise for you, Krishan, to go in and actually check that if you have two categories and you look at the category of functors, but between them that like, or sorry, if you look at the set of functors, that it is still a set.
Um, one has to be a small category, like the source. Here, the
Yes, 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 yeah, yeah. I mean, everything we're doing is small so far. So yeah.
okay. Okay. You are bullying me into believing this is
No,
a
no,
set. So
no.
okay.
Like,
Okay, it's a
I mean,
set.
it's
Fine, fine.
there's some data like there's some writing down you should do. Like you should go and actually like try to write down the data that describes what a functor is, right? And
Yeah, yeah.
like that's what this is you're doing here. You're just like writing down how you parameterize this. You write
Mm-hmm.
some really big set that is like, and you write some condition on that really big set of possible functors, and you
Uh-huh.
characterize like when they actually are, and so that they end up just being inside of some set, and so it's still a set.
Okay, 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 okay,
so
okay.
if you're concerned with the size issue, you could
Yeah,
think
yeah,
of
I'm concerned with the size. Yeah, yeah.
okay, that's pretty easy. So if you believe product, um,
Uh-huh.
infinite many product of set is still a set. Like it's
Uh-huh.
not so many infinite. It's just a natural number many things
Product,
product.
yes,
It's
yes,
still a
yes,
set.
yes.
Now
Yes.
you can consider all the maps between sets of x0 to y,
Okay.
x1 to y1, and
Uh-huh.
just all of the maps between two sets is a set.
Right.
So
Right.
it's like a product of many set
Got it.
together.
Got it.
It's
Got it.
still a
Got it.
set. Then
Got
we
it.
take a subset who is like
Yeah.
the satisfying the
Got it. Got it. Got it. Got it. Got it.
commutative.
Makes sense. Makes sense. At each level, this is a subset of a. Okay. Makes sense.
Yeah, yeah,
Yeah.
yes.
Yeah. 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 So it will be a. Yeah. Okay. Okay. Yeah. 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 Mm-hmm. I was concerned about. So for now, at least I can see if both of them are small categories, then this will work. Okay. 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 Yes, I was concerned exactly about that. Honestly, like.
Okay.
Okay. Yeah. Makes sense. Thank you. Thank you for the logic. Yeah. Um. Yeah. I think this can be a good point to stop. I will just define the composition here in the mapping space, and we can stop here. or I can keep going if you want me to keep going.
I mean, I think we're already like what 15 minutes over.
Okay, okay, okay.
Very nice.
Oh, I defined the composition here, but I did not define what a composition is. So that's on me. Okay. I use the composition over there, and actually I use the product as well over there. So for defining the homotopy, so that's on me. So this is how we define the composition. So take a map
X.
G, take a map F. So your F is the map from um F is the map from here to here, X cross delta Q2 um Y. G is the map from X cross delta M to Y cross delta M to Z. Now I want to define G compose F such that it lands in here. So I want this guy to go from X cross delta Q to Z, right? Now how do you go there? In terms of this F and G, for that you use the diagonal map. X cross delta Q to delta Q. Now X cross delta Q to Y, we have the map. What is the map? We have the map F cross delta Q, and Y cross delta Q to Z, we have, okay, F cross identity, because delta Q has to map to here. And Y cross delta Q to over there, we have the map G. And take this composition, this G compose with F cross ID, compose with ID cross delta. That's your composition map from here to here. And I think this is a good way to stop. So far what we have done is define homotopy. At least we have done the first thing. Homotopy in terms of, where is the homotopy? Here. Homotopy between two simplicial sets in terms of simplicial sets. And we have derived the notion of mapping spaces in terms of simplicial set. These are the big two notions. We started with this F guy, ended with this mapping guy, started with this homotopy, ended with the homotopy. So yeah, I do think it's a good place to stop here. Yeah, that's,
Okay, thank you for your talk. It's great.
yeah.
What are you planning to talk about next?